Hi, I'm Ben-Yaakov. This presentation is entitled A Primer to Wireless Power Transfer. Now, the idea of wireless power transfer is not new. Actually, the first indication of such an idea has been published by Nikola Tesla in 1898, about 120 years ago. And here it is. There is a primary coil. This is a capacitor for actually creating a resonance here. This is a generator. There's a secondary coil. And these are the output terminals. Actually, this was for a therapeutic purpose for healing people. This has been very popular at that time. Now, later on, this idea was actually explored, and here is a suggestion for an experiment. This is in a do-it-yourself journal, Practical Electrics. And here they suggest how to build a wireless power transfer. This was published in 1921. And here we have a transformer. This is the AC line. This sparker generates pulses, high current pulses that go through this resonant circuit. And then we have the secondary coil, and lo and behold, you have a lamp which is connected, and it will light when this will be in operation. So this is really not new. However, today, of course, the electronics capabilities make it much more practical. Now, for Tesla, the idea of wireless power transfer was not just a technology, it was sort of a ideology, because he was concerned about universal peaceful relations, and he believed that this could be achieved by annihilation of distance, and to achieve this wonder, electricity is the one and only means. Okay? Well, this is really very idealistic, and unfortunately, I don't think it materialized as yet, maybe in the future. Now, let's go back to ground. This is a very simple presentation of the wireless power transfer. We have a primary coil, which is excited by, say, an AC source. As a result, there is a current here, and the magnetic flux is created, and it's getting all over the place. Now, if we'll put another coil close to it, then part of this flux, K fraction, will enter this coil and will generate a voltage. And by this, we'll get the wireless power transfer, because we have power from here going through here to here. So K is really a very key factor here. This is the coupling coefficient. This is how much of the total flux generated in the primary is actually reaching the secondary. So if we have a K fraction at the secondary, and if the turns ratio is N2 here and N1 here, we are going to get this voltage ratio, K times N2 to N1, which can be also expressed as a square root of L2 over L1. Now, obviously, K is always smaller than 1. It may approach 1, but it's really never 1, because there's always some flux which is escaping, even if in a transformer which is wound on a magnetic or ferrite core. Now, the way to model a system like this actually can go two ways. One is use this mutual inductance concept. We have two inductors which are coupled here, or we can use a transformer representation. Here we have a transformer. This is a model of a transformer. We have a leakage at the primary, a leakage at the secondary. This is the primary inductance. And this is now ideal transformer that just accounts for the transfer ratio between the voltage and the current. So there are actually two ways to go. And in fact, in one occasion, it'll be easier or better to use one model, and in some other applications or analysis, it'll be easier to use this one. So if we have this mutual inductance between two coils, then this implies that at the primary you have an inductor, L1 is the original inductor, and then you have a dependent voltage source which depends on the current on the secondary. This is the current in the secondary with the mutual inductance value here. And the same thing goes for the secondary. You have a dependent voltage source, the magnitude of which is j omega, m is the coupling coefficient, and I1 is the current here. Now m, this coupling coefficient, again is a function of the coupling coefficient. This is the most important parameter in these situations, and square root of L1 times L2. Now, in the case of a transformer, and now I'm talking about a one-to-one transformer because in many applications, L1 and L2 are the same type of coils or inductors. So for n equal to 1, I can eliminate the ideal transformer here because it's a one-to-one. And what I'm left with is the two leakages and the inductance, the common inductance. Now, this is reflected to the primary. The leakage inductance is L1 times 1 minus K. K is the coupling coefficient. Now, if K is 1, this is the ideal case, there is no leakage, and all that we see is this common inductor. K will be 1, and we see L1. Now, as K is becoming smaller and smaller, we see here larger and larger leakage inductances, and this inductor, however, becomes smaller and smaller and smaller. See, K times L1, so if K is, say, 0.1, then we are left with a small inductance here. Now, in the case of a one-to-one situation with the mutual inductance, we have similarly two inductors, which are the same in this case, and two voltage sources, which again are dependent on the current on the other side. So here it is here, and here it's a function of I1. So what's the objective of wireless power transfer? First of all, we like to transfer as much power as we can. This is, of course, the purpose of the whole thing. And another one, which is the key factor, is efficiency. We like to do it at as highly efficient process as possible. Now, what are the problems that are involved? First of all, the distance. Larger distance causes a small coupling coefficient, and therefore you get only a fraction of the flux, and therefore you have somehow to handle the fact that a lot of the flux is actually being lost. There is the issue of parasitic resistances, which are causing losses and reducing the efficiency. And also there is the question of the large apparent power. This is the product of voltage times amp. Now, you'd like this product to be very close to the real power, because if this apparent power is large, it has many implications. One of them being the fact that you need larger reactive element, that is inductors and capacitors, because they have now to store more energy. Another implication is that you get a higher losses since higher current will pass through the source. So you'd like to keep the apparent power as small as possible. Now let me talk a little bit about resonant circuits, because we are going to use this approach in order to improve the coupling between the coils. So in this case, we are talking about two possible resonant circuits. One is a series one. Here is a series one. L, C, and R, this is the load, or parasitic resistance if there is no load. And here is the parallel one, L, C in parallel, and this is the current source. Now, there are key parameters that we need to address. The circular resonant frequency, 1 over square root of LC, the resonant frequency, omega times 2 pi, the characteristic impedance, the square root of L over C. Now, another key factor, which is very, very important in the wireless power transfer, is the Q, that is the quality factor. Now for the series circuit, it's defined as omega L over R. Now notice that this is really the ratio between the apparent energy or reactive energy to real energy. Because if you multiply it by I square here and I square here, this will be the energy stored in the inductor and the real energy. Now you'd like Q to be large on the one hand because you'd like the circuit to have a sinusoidal waveform. This helps zero voltage switching and some other features. However, a too large a Q means that this energy here is very large, so you need large reactive element. So we like to keep Q really in a reasonable range. I'll talk about it in a second. Now you can express the Q, the quality factor, as this ratio, or 1 over omega RC, or the characteristic impedance over R. Now in the case of the parallel circuit, it will be 1 over, it will be R over omega L, and it will be R over ZR. Now, in this case, in the series case, when R approaches 0, then you have a very high quality factor. In the parallel case, when R becomes infinity, then you have a large Q factor. So these are the basic concepts of a series and parallel resonant. Now, we can use now the resonant circuit in order to reduce the total impedance in a circuit. Now, if we have a branch like this and we are at resonant, the total impedance here is 0. So when we have here resonance, we are going to see from the source only R, because these two cancel each other, the impedances. Okay, this one plus and minus. And the same thing goes here. At resonance, we're going to see only R. So we are going to use this to our advantage in the case of the wireless power transfer by adding capacitance here. Now, why would you like to do that? Because otherwise we have an inductance, and this is actually limiting the current that will be passing to the output. So by putting this capacitor here, I can, and when working in the proper frequency, I can reduce the impedance of this branch and allow more current to go to the load. So you can see it all here, and you can see it here. We add here, in this case, 2 capacitors. Notice that the resonant circuit are not very clear here. I mean, I can talk about these two, but then we have this inductance, which is also apparently playing some role. We'll talk about this a little bit later. So, in a very simplistic way, you can say that if you put a capacitor and you work at resonant, then you're going to see in this presentation of the transformer a inductor K times L and RL, and obviously now part of the current we see now it here is passing through here, and you are losing some of the primary current. So as K is becoming smaller and smaller, we have a problem in transferring power to the load. Okay, so we need a high current. Same thing goes in this representation of the mutual inductance. Obviously, here we have K. The smaller the K, the smaller is this dependent voltage source, and less power will be delivered to the load. So, what about the efficiency? Efficiency is the output power over the total power that's coming from the input. And the input has to supply the output power plus all the losses. Now in this circuit, in this equivalent circuit, the losses are due to parasitic resistances. And these include, first of all, the driver. These are the MOSFET, RDS-on resistors, the parasitic resistance of the inductor, the coils, ESR equivalent series resistance of the capacitor, and the same thing goes there. So the efficiency will be the ratio between the real power, IN is then normalized I2 to I1 and divided by the total actually power, which is this is the contribution or the loss due to the parasitic resistance of the primary. This is the secondary, and here is the load. So in order to have or get high efficiency, you'd like to reduce RL first of all, and this could be done by using Litz wire, so that the RAC, as it is called, that is the resistance at high frequency, will still be fairly acceptable. You need a low ESR capacitors, and of course the driver should have a low RDS(on) transistors so that RS, this equivalent resistance, will be low. Let me just point out that this circuit, although it looks very sort of simple, it is really complex because there are many interactions here. As I already mentioned, this inductor here plays a role in the resonant of the secondary and primary, and therefore a complete analytical study of this circuit is really complicated, and it leads to rather long equations. This is not the purpose of this presentation, which is an intuitive look at the whole issue of wireless power transfer. Just to get a feeling of what's all about here, let's consider two cases. Let's start with this case. Let's assume that the RL is very high, and that's representing it by an open circuit. Well, here you see we have a resonant now here. There's nothing here, so the resonant frequency will be C1, and the total, which is, by the way, the original primary inductance, because this plus this is L, okay? And if you drive the circuit at this resonant frequency, you get a very high voltage here, more than 1. I mean, the ratio will be more than 1. And then if you have a high resistance here, you'll get quite a bit of power. So this is another mode of operation, having a large resistance here. If the resistance, however, is very small, and I'm representing it by short, notice that we have now here a sort of a network, which is sort of a resonant network, and plus another network. It's not a simple circuit here, and of course there are many resonant peaks that you can detect at various frequencies here. So in order to simplify the understanding of the circuit, I'm going to do some simulation and present some of the results just to show the behavior of this circuit under various conditions. And the circuit I'm going to simulate is this circuit. Two inductors which are equal, they are 86 microhenry, with two capacitors which I'm going to change later on. There is the AC source, and I'm going to do two types of analysis, an AC analysis. For this you need an AC source, and I'm going to do also a time domain analysis, a transient analysis. For this you need a transient source or time domain source, and I'm going to use the V-pulse just to feed it with a square wave, as you would do with a driver in a practical circuit. If the capacitor is 29.45, the resonant here is 100 kilohertz. The characteristic impedance of this circuit is 54 ohm, and just for the sake of the numerical analysis, because simulation is numerical, I'm assuming a 10 milliohm parasitic resistance at the primary and at the secondary. So I'm going to do actually two types of simulation. One, assuming that K, the coupling coefficient is 0.5, so this will be sort of the equivalent circuit that we consider. This is 0.5, should be L here too, and this is 0.5. And then I'm going to use two capacitors, one C, this is the capacitor that for 100 kilohertz has a resonance for the whole inductor, and 2C, because 2C plus half L is giving a resonance in here, okay? And then I'm going also to run a simulation for K.1, and we have then this is 0.1 L of the original primary or common inductor, and this is actually approaching already L. Okay, so this is very small, and these are very large, and I'm going to run it for the 29 nanofarad capacitor. Okay, here's the schematics of this circuit there we are going to run. Let me zoom on it so we can see it better. Here we see the two inductors which are coupled. We have here the K linear, the element that is coupling L1 and L2. This is L1 and L2. They are 86 microhenry. Coupling coefficient is 500 milli, that is 0.5. We have here two sources. One is an AC source. This is for an AC analysis, small signal analysis. And then we have a pulse type source. It's a plus minus amplitude and with some rise time of 0.1 microsecond. And the pulse width and period are adjusted so that the frequency will be like in this param frequency. Here it's defined as 100 kilohertz. We can change it. And the duty cycle will be 1/2. Okay, so the two capacitors are defined by parameters. This is just an initial value. We're going to change it. And then we have a resistor. This is the load resistor, which is also defined here. It's 54. We're going to change it right now. And we have some parasitic resistance here and here. I've just specified it to be 50 milliohm. So let's change this one to, say, 1 ohm to begin with. And let's see, let's run the AC simulation. Let's see what is actually is the setting here. 10 kilohertz to 300 kilohertz, 1000 points per decade, so we have a good resolution. And we have a parameter switch of C, and I'm going to do a value list. And so these are two values. This is the 29.45 nano and 58.9, and these correspond, the 29 is for this resonance, and the larger capacitor is for the model in which for a coupling coefficient of 0.5 we are going to have the leakage. It'll be 0.5 of the inductor, so therefore we need a capacitor which is twice as large. Okay, so let's start with this AC analysis. Let me first of all have a look at the first capacitor. This is the 29.45 nano, and I've set up scales as follows. We have the inductor, the input current, inductor current. We had the output voltage. This is across the load. We have the power of the load. This is the power. And we have actually the efficiency, which is the power on the load divided by the power that comes off the source. Okay? Now this is for, let's remember, 1 ohm load, and the capacitor is 29, so that the resonant is between, supposed to be between the total inductance and the capacitor. What we observe here is really much different. To begin with, we see two peaks. One at, this will be a little bit over 140 kilohertz, and this one is a little bit over 80 kilohertz. There are two peaks here. This is the, say, the output, and of course you see the current at the input. Okay, so we have sort of a split phenomenon in which the supposedly one resonance is split into two, and again this is because there is an interaction between all the components in the system. Okay, and if we look at the output, we see that we have a fairly high output. Remember, I didn't mention it, but the excitation is 1 volt, okay? 1 volt. So we have a 1 volt output is about 1 volt, and the power is a little bit less. I don't know why. Supposed to be 1 watt. Maybe there is a difference here between peak and RMS values. I am not so sure. So then we look here at this is sort of an efficiency. We see the efficiency is fairly high. Remember, we have parasitic resistances of 50 milliohms. The load is 1 ohm. So relatively, the losses are not that high. Interesting enough, we have another peak here for high efficiency, and this peak indeed is at 100 kilohertz, okay? But this peak is at the point there is virtually no output, or let me say that the output is very, very small, okay? And then the input is small and the ratio between them is pretty good. But this is not a useful point. So the conclusion here is that for 1 ohm with this capacitor, we have 2 peaks at frequencies which are different from this 1 kilohertz, and we get a pretty good transfer function with this zero point 0.5 coupling coefficient. Let me now go back and have a look at the situation for the 58.9 nanofarad, okay? So I'm selecting this value. And well, the picture is not much different except that the old frequencies actually shifted downward. Lo and behold, we have now a peak at 100 kilohertz. There's a peak here. We have a peak current at the input. We have a peak output voltage, and then we have a good efficiency. But then we have another peak at a much lower frequency. This is supposed to be, this will be 70, above 60, close to 60 kilohertz. There's another peak. And for this peak, we get also a pretty good result. However, this high efficiency is really useless because at this point we just don't have any output, and of course there's no input, okay? So this is the situation with the capacitor, which is twice as big, so that the resonant is between the capacitor and half the inductor, half the size, the value of the inductor. Let me now move to the case of a different resistor, and let me put this one to be like 27 ohm. You remember that the characteristic impedance of this circuit, calculated just by this inductor and this capacitor, which really doesn't tell the whole story, but if you use these to calculate the characteristic impedance, it comes out to be 54. So we are now at a value which is like half, so we're going supposedly having formally a Q of 2, okay? So let's run this one now, and I'll pick the first one, and wow, we have a whole different story here. As you can see, the sort of Q of 2 is causing this circuit to look very flat. This is the efficiency. It's very high here, but again, one has to look at the output. But unfortunately, the output as far as the power goes is not very good. Indeed, we do get a fairly high output voltage above 1. That is, we have actually a gain above the input. But since the resistor now is much larger, it's 27 as compared to 1, then obviously these square over R, which is the power, is now much lower. And indeed, we're having only like 50 millivolts. So we have a problem here in terms of the amount of power that we are delivering. But note again that this flat behavior that kind of suggests low Q circuit. Now, let me now go back and change the resistance even farther. Let's make it, let's say 100 ohm and run it again. And we'll choose again this 1929 nanofarad. Well, we have a different story here. We have one resonant, and it is at 100 kilohertz. This is because we have now a resonant. This is like an open circuit at the output, which I've shown earlier one of the slides. So we really have a resonant between the whole inductor and the capacitor, and we know this should be at 100 kilohertz, and indeed it is. We have a output which is fairly high because the Q is high, and this is now like a parallel circuit partially, and we have a higher voltage, but still the amount of power that we get out is not very much, is only 120, 50 milliwatt. At this point, however, the efficiency is fairly high because now we have a much larger load resistor as compared to the 50 milliohm of the parasitics, then of course the efficiency will be high. Okay, let's do even a larger, make a larger resistor, say 1 kilo ohm, and then of course we are just about at the, and this is indeed like a open circuit. The Q is much higher now, like a parallel circuit, and the output voltage is much higher. Let's see that we get a much higher voltage. We do have now a fairly high output power. This is above 1 watt, and this is because the voltage is very high. And so that that's 40 squared less than 40, 30 something divided by 1 kilo ohm is again 1 watt. Now the input current in this case is not that high. It's about 1 amp. It's a little bit more than 1 amp. And 1 amp would be the power required for 1 watt, and this is a little bit higher. So we see that the VA, the apparent power, is not that high as far as the input source is concerned. So what really this teaches us that the situation is really complex, and you have to look at your particular load resistor and match it to the configuration of the circuit to get an optimum result. Let me move now to the case of the 200 milli for the coupling coefficient, that is 0.2, a K of 0.2. And let's start off with, say again, 1 ohm here. And we see pretty much a similar situation. Maybe the frequencies that are a little bit different. You see these two peaks are closer one to another. Again, we have this strange high efficiency point with no output power. But the situation is not very different. And just for a check, let's have a look at, say, 10 ohms here. What is happening? Okay, now obviously this total apparent quality factor is worse. These two peaks are sort of getting closer, and as you see here, the minimum now is not 0, it's going up, and we get the same gain, just about the same gain. However, since the load resistor is much higher, it's 10 times higher, then the power is about 10 times lower. So we get good efficiency, but the power output is low. So the conclusion here again is that you really have to tailor the load to the particular circuit, and there's no one solution for all loads. Let us now look at the transient response, that is the time domain. Remember, we have here a square wave excitation, so I'm moving to a transient setting, and let's see what is the setting here. We are running it for 5 milliseconds, collecting data after 4.95 milliseconds. This is the resolution, and the parametric switch is again these two capacitors. I'm now back at the AC, at the result of the AC analysis. And the reason is that I like to select the operating point. So let's start with this 100 kilohertz, which is right here. This doesn't seem to be the optimum point, but let's just see what's going on here. Now running it, and this is for a frequency of 100 kilohertz. Okay, let's choose again the 29.45 nanofarad, and here it is. And this is now the output voltage. As you can see, you see a nice sinusoidal waveform. This is the excitation. This is the current of the input, and here we have the actual power. This is the product of the current times the voltage on the load resistor, okay, and averaged. So this is now the power, which is not very good, okay. So let's go back to the AC analysis again and run the, say, this is the AC analysis again, and let's run the 1 ohm case again, and the purpose of which would be to find the frequency, okay? So I'm turning on the cursor, and let's have a look at here. I look at the frequency, and this is 110.63. Let's say 111 actually, 111 kilohertz. This is this frequency, okay? So I'm returning now to the circuit, running a transient analysis, but changing it to 111K and run it. Okay, I'll choose again this 29 nanofarad, and here what it is. So we see that the power is now higher. We have a nice sinusoidal waveform because of the nicer Q. So here we can examine the actually time domain waveform of this. Okay, let's go back now to some real circuits and see how we actually implement this wireless power transfer. Now this would be a very simple realization. We have here a half bridge driven, of course, out with 180-degree phase shifted pulses. Here is the primary. This is the secondary. We are talking about this resonant circuit, and we know that there are some implications and questions, but let's leave these aside. Just look at the circuit itself. We have now a rectifier, and we have a smoothing or filter capacitor plus RL, which represent the load. Now, in the analysis, we have been using any resistor. So it'd be useful to replace this. This is a non-linear circuit that you cannot use in AC analysis. It'll be useful to replace it by an equivalent, as we call it, RAC resistor. That is, I like to replace this whole thing by some resistor such that the circuit will behave the same as far as AC analysis goes. Now, the way to do it has been demonstrated many years ago by Professor Steigerwald, and the idea behind this representation is to equate the power. That is, you like to select a RAC such that the power delivered to it, or consumed, or dissipated by it, is equivalent to the power dissipated by this DC current through this RL load. So here is the AC side power. This is the unknown yet resistor. This is the DC part. Okay. Now we can now express IDC as a function of IRMS through the peak and the average value 2 over pi, and then from which we get this RAC it's about 0.8. Pi squared is about 10, so it's 0.8 RL. So you can replace this whole thing by this, and this is very helpful when analyzing or simulating, in fact, the circuit. Now, there are some other situations which are practical. For example, if you are charging a battery, then you cannot represent this load by a resistor. It is a fixed voltage, and you may change the current. So again, by equating these two, power on the AC, power on the DC, we get this RAC expression, and in this case, it is a function, well, you can make it a function of the DC current charging the battery or the primary AC current. So it's a non-linear resistor depending on the operating point. But for a given operating point, this is the value. For a given, say, charging of, say, if it is a battery, 4.4 volts, 1 amp, then you'll get 3.6 ohm resistor RAC equivalent that you can use for the analysis. Another case is when you feed the battery with a constant current, so this is a power type of a load, but then again, since you have the current here and V battery is very similar to what we had before, so you end up with something very similar as we had before. So this is the way to represent this nonlinear rectifier plus load by an RAC. Looking now at the bigger picture, it turns out that this case of resonance, series resonance at the input and output is just a private case of many other, not many, but there are other possibilities. We can have a resonance, series resonance at the input, series resonance at the output. We can have series at the input, parallel at the output. And we have parallel at the input, and series at the output, and of course, parallel and parallel. Now, what's the advantage and the problem with any of these connections? Now, when you have a series resonant at the input, you have a fairly large apparent power, and you have all the current passing through the source. So the RDS(on) of the transistor sees all this current, it could be high. So in the output, you have this resistor in series with this resonant circuit, and obviously to get a reasonable Q, RL has to be smaller than the characteristic impedance, so this leads to fairly low values of R. Okay? In this case, in the second case, this would be suitable for loads which are represented by a large R, so that you can get a high Q at the secondary given a certain value of characteristic impedance of L and C. And this again suffered from the same thing. Here we have an advantage in that we can generate a very high current at the parallel resonant network, this here, while this current is circulating here and not seen by the source. By the way, for a parallel circuit, this has to be a current source, because if it is a voltage source, then obviously you are imposing a voltage here, and the resonance doesn't take place here at all. So for a parallel resonant primary, you need a current source. Secondary, again, we have here in series, and here again we have parallel and parallel. So this will be helpful to eliminate the high current through the coil from passing through the input. And here, this would be suitable for a high value resistance. I mean, high value compared to the characteristic impedance of the secondary. It can be concluded that the parallel connection at the input is really desirable under all cases because it can generate high current, which is locked in the parallel circuit, not passing through the input. As for the output, it really depends on the type of load. One way to do it is to use this network shown here. This is the coil, primary, the input, the output coil, and this is a series inductor, should be fairly large, and this sort of imposes the current into the circuit. As it turns out that this circuit is really not easy to control, and also you cannot very easily control the switching losses under all operating conditions. So this has not been used, as far as I know. It's not been very popular. Another circuit, which is very interesting, is a so-called push-pull parallel resonant inverter. And there are two configurations, and I'll start with this one, which is the original one and has been around for many years. We have here a parallel circuit, parallel resonant circuit, which is center tapped. Okay? And then again, we have a series resistor. These transistors are operated in 100-degree phase shift, so that when this pulse is high, this is low, and vice versa. When this voltage is high and this transistor is conducting, so this point is connected to ground, and since we have a feed here of the source, then we'll start generating a sinusoidal waveform of this at this point, the other side. This is ground, and this is the other side. As we hit this point, this should be now pulled to high voltage and clamp this to ground. And then, of course, we'll start generating here a sinusoidal waveform going up, like here. And again, as it will approach zero, we change the situation, and this will be on, and this will be off. So we need, of course, to synchronize these two with the waveform, and we are going to have then interleaving one side, the other side, etc. Over the coil, over the inductor, we're going to have a sinusoidal waveform because we have sinusoidal waveform half, 180 degree to one side, 100 degree to the other side, so we have a sinusoidal waveform. Another configuration is this one. Here we don't have a sensor tape. If it's not convenient, if we don't want to have it, we have these two inductors which are passing the DC current to this inverter to power it. Operation is very, very similar. We have this sinusoidal waveform generated as one side is going to ground, we have it on the other side, etc. So this is really very similar, except for the fact that we don't have a center tap. We pay for it with two inductors instead. Now, it's interesting to realize that the current that is passing through this inductor or through these inductors is primarily DC current. There's some ripple depending on the size of LS. As large as it will be, the larger will be LS, the smaller will be the ripple. And this DC current times the voltage is in fact just the real power coming off the source. So we have very little AC current passing through the source, which is very desirable. Same thing goes for these transistors. These transistors see only this current. They don't see this current. This current is not seen by these transistors, I mean the resonant current. So you can build up a fairly high resonant current without this transistor passing it, which is very nice. They are passing only this current or this current. Okay, this is the DC current which are passed through the transistor. Transistors do not see the AC current, which could be very high, which is very nice. Finally, let me say a few words about ways to enhance the coupling and to increase the coupling coefficient. And one method that has been suggested is to add some ferrite elements in the construction. And this is just one example. There are many examples that have been published and been practiced. Here we have the primary. Here we have the secondary. Now these are ferrite bars, okay, ferromagnetic bars, ferrite. And what they do is actually they sort of channel the flux to this direction. Rather than the flux going all the way to everywhere, they are sort of channeling it. So if you place the secondary coil, the receiving coil, sort of around this, of course there are bars here too, I'm just not showing it so as to confuse the picture. So as this secondary is placed over the primary, it'll capture these channeled flux lines, and therefore it'll have a coupling coefficient which is much larger than you'd have without these bars. Okay, so this would be one way. Another way is actually to put a plate of a ferromagnetic material underneath and in fact above, okay, so it'll lock the flux in between. These are two different ways, and there are of course many other ways to do. This brings me to the end of this presentation. I thank you for your attention. I hope you have found it of interest and that it'll be useful to you in the future. Thank you.